We've seen in lecture 11 that MRI, or magnetic resonance imaging, is a technique that's very sensitive to motion. There we introduced it as a problem in the sense that it creates corrupted data sets. Now usually when there is a problem with magnetic resonance, then there is usually also an application. And this is what I want to talk about first. That is the effect of motion on the signal, and in particular here on the rephase signal. We're going to first talk about bulk motion, and later we're going to talk about random motion today. So, what is bulk motion? What are we concerned here with, or what are we interested in? Here it's an example of an angiogram. It's blood flow. We have the blood vessels depicted here. This is an MR angiogram, obtained completely non-invasively. A depiction of the blood vessels here in the brain. What is bright are the blood vessels, and the stationary magnetization, that it doesn't move, has been suppressed from this image. So let's look at the phase of the magnetization to understand how this can be registered. The phase of the transverse magnetization as a function of time is given by the transverse magnetization at time 0 times e to the I phi of t. This is in a complex plane, so we denote, as usual, the real part, for example, is the x component of the magnetization, and the imaginary part of this number is, complex number, is the y component of the magnetization. Now, here we have written phi of t, so it's a time-dependent phase, and the question is, what is this phase? And this phase, in very general terms, we have seen is given by the integral of the gradient times the position with time. There's a gamma in there, of course, to get the phase. And this particular example, this equation here, is for the case of a gradient along x. Here t prime denotes the integration variable, just to distinguish it from the time t, which is this variable here. That's the integral from 0 to t here. So this is the phase that we obtain. That's the general expression. Now I'm going to, and you will see shortly why, I'm going to now write the phase of t, this integral. I'll split it in two integrals, so there's two time periods, one from 0 to big T, where the gradient along x, and we'll stick with x here, is along x is gx, and then we have a time period, just subsequent time period, from time t to 2t here, where the gradient is minus gx. So we basically are depicting an experiment where the gradient is first positive, and then at time t switched to a negative value. And this is what we're looking at. Now here this is just negative is first and then positive. It doesn't make a difference what the sign here is. The sign is really not important. So this is the gradient along x. What we see, the phase evolution as a function of time at time 2t is given here by this expression here. So small t here is equals to big 2t, 2 times big T. Now what we're going to express here is the position of the magnetization that we have in the voxel. Normally we would describe it as a stationary magnetization. That's what we've dealt with so far in lecture 11. Now here we're going to assume that this magnetization in our voxel is moving at a constant velocity v. So the position as a function of time is now no longer constant, but it's given by x0, the original position, plus v times t. And now we'll write the substitute x of t in the above integral. So we'll substitute this expression in here, and we'll obtain these two integrals. We can now see that this integral here and this term here, they are the same. They're constant in time. The interval is t, so these two terms will subtract out the stationary magnetization due to stationary magnetization, and that is the condition of echo formation. So I'll just be concerned with the term that is dependent on the velocity. Well, here we've kept actually the constant term in here, and we'll take this term here. Here's the integral. So here's the constant term. This is negative, this is positive, same value from 0 to t, and from t to 2t. So the difference in t here is t. So these two terms cancel. So we're just concerned with this term here and this term here, and you can verify here very easily that these terms now no longer cancel out to 0. And the consequence is, we do the integration here, I won't do it in all details, that we get a phase at time 2t, big T, which is given by gamma g, the gradient, times the velocity, times this time squared. So we have a phase now of the magnetization that is changed depending on the velocity in the direction of the gradient and the gradient strength, as well as the duration of the gradient application. So we'll look now graphically the implication of this. We'll first have the phase, plot the phase as a function of time. We'll first consider a stationary voxel, so no magnetization moving. Here's the phase on the vertical axis. On the horizontal axis we have time. And as we move through time with the gradient, phase goes first up with a constant slope, that's the constant gradient, and then comes down after another time, big T. So we have the times here indicated. 0 is at the beginning where the gradient is turned on. The big T is the time where the gradient polarity, that is the sign of the gradient, is changed, and 2T is 2 times this time. So this is for stationary magnetization. This is the case we've discussed extensively in lecture 11 and a little bit in lecture 12. We have, of course, this condition that the phase at the end is 0. Here, the phase comes back to the same value as it was here. This is given by the fact that for a stationary magnetization, the integral of the gradient here, the area, total area is 0, or this area is equals to this area, and this is echo formation. So this then defines the echo time TE. Now, if we consider blood moving with velocity v, so here's the blood, we have our magnetization in the voxel, and that is now moving with velocity to the right. As this happens, as it moves, we are accruing a phase, and then we're losing the phase again. But at the end, we have a difference in phase compared to stationary magnetization. And this difference in phase here, phi of TE, this phase is dependent on the velocity. So it is a measure of the velocity of the moving blood in the direction of the gradient. So it comes from, in the integration, it comes from these two terms here that don't cancel out. In this integral, the stationary magnetization, the phase cancels out. So if we look at the transverse magnetization at a point xy, then the magnetization at this point is proportional to e to the I times the integral of the gamma g times the position. Here it's gradient along x, so that's this expression here that we are using here, and this is equals to the k-space. That's the normal image formulation that we've had for stationary magnetization. Now, the phase that is induced by the motion does not depend on the position. So that means basically for a given velocity in the direction of the gradient, the phase in the voxel will change by the same amount of radians or degrees independent of its position. So this is position independent, so it's a direct encoding of the velocity, and that means that the entire echo, if all the magnetization is moving at this velocity in the direction of the gradient, has a phase phi at the time TE. So we can now write the magnetization at a position in the voxels is proportional to e to the I phi, and phi here is given by the expression on the left. By this expression I've substituted 2t with TE, so now we have the term here. So for obtaining images like this is one way to obtain encoding of a velocity in the voxel. For such an image, one can obtain the encoding of the velocity, not just the velocity, but also the direction, it's along the gradient, by simply recording the change in phase compared to stationary magnetization with appropriate reference scans. So we see that motion affects the phase of the voxel. So this is now coherent motion. We've assumed that the entire voxel, the magnetization in the entire voxel moves in a certain direction. Now what we're going to be concerned with is random motion. This will be the next section.